I have a few questions for our panelists, and then I'll turn to the audience for questions. So you should all be thinking about what questions you'd like to ask our terrific panelists. Dorsa, let me start with you. If we're dealing with systems that can hurt people or hurt themselves, how do we go about training and testing things where we can't really leave them to operate freely?
So you're saying, wait, can you actually say that again? So you're saying you have systems?
Sure. Well, if I have a robot or a car or something else and I'm trying to train it, say, to interact safely with humans, obviously I don't want to injure the human along the way. If I have an autonomous vehicle, I don't want it to crash into a fence or drive off a cliff while I'm in the process of training it and testing it. So how can we create safe environments for training and testing?
That is actually a very good point. So we do a lot of simulation. So there's a lot of work in simulation that we try out, and we can try all these unsafe situations in simulations, right? And that's the very first thing we want to do. And then there's also a lot of work from simulation to real world, like how to create really good simulators that can show the real world effect of it. So that's definitely the first thing we want to do. The second thing actually is the fact that this kind of connects to the safe exploration and safe learning ideas that I was talking about. So we can't, like in real world, like if I have a robot, we can't just like explore everything because I'll lose a robot every time. Every time I try a counterexample, I lose a robot there.
So how do you actually do this? Do you create code that creates
a safety
fences
zone
where you can't go outside of
so
fences?
the idea is we want to start conservatively. We want to start with a safe set. And then as we are kind of like how, let's say you have a hot object here, and if you want to hold it, you don't just go and hold it grab it all together, right? You start nudging in. So you can create this safe set, and you can start nudging in around your safe set and expand it as you go. So that's kind of an approach that we can do. And we'll have uncertainty around the boundaries, but as we get more and more information, the point is to reduce the uncertainty around the boundaries.
Are there other techniques for safe testing, or is that pretty much it? Mykel, Justin?
Well, as I say, one of the things, so I don't have a lot of direct experience with vehicle automation, but the Insurance Institute for Highway Safety and the Highway Loss Data Institute, which are two pretty prominent organizations in insurance, have gone big on crash avoidance technology. And so they've invested quite a bit in robotics and track testing, where they've designed hundreds and hundreds of different experiments with children walking across roads or dummy vehicles that come at certain angles, all for the purpose of testing the crash avoidance technology. So
sure, but if we talk about the kind of software you're going to use inside an insurance company, don't you also have the ability to have things running in a way where they're not actively making decisions, but they're running alongside your legacy or human systems, and you can see how they work?
Yeah, absolutely. I mean, most of them...
do you do that?
Yeah, most of the models that we build, after, of course, training and testing and validation and whatnot, run in some sort of pilot state. And maybe that's, we test something with our agents before we go to customers, or some sort of other captive audience in that way, or we'll pilot it in just a certain area of a state before going nationwide. Lots of different ways to sort of parallel test things.
Mykel, did you want to comment on this?
Yeah, so I think two things. For safety critical things, you absolutely have to rely upon simulation, but it's really important that your simulations are representative of reality. So you need to capture the same kinds of statistics that you see in the real world. Otherwise, you can significantly overestimate or underestimate the risk. I think one other point that I should make that's connected to this is that if you spend all this effort building a high fidelity model, it's really tempting to use that model to inform your decision making directly. And that's a form of overfitting. So overfitting is well understood in the context of supervised learning, but it can also be a major problem in when you're designing these safety critical systems.
And if I understand you correctly, the problem is a kind of circularity. If we're testing the system with the same data that we use to train the system, we're not really testing it, right?
That's right. And you can significantly overestimate the safety of the system if you do that. And so it's important to keep the two kinds of models, the planning the planning model and the evaluation model. You want to keep those independent.
But how do we do the things that Mykel just described? How do we create high-fidelity models, and how do we make sure that we really are testing our systems in representative scenarios? Gee, I didn't expect to stump you this early in the discussion.
So maybe I'll start while you guys
Yeah.
think about it. So actually, before we started the ACAS-X program, we worked on building these high-fidelity airspace encounter models. And in order to do that, we had to collect a huge amount of data. So 9 months of all the FAA and Department of Defense radars, we had a continuous stream of this. This was about 15 gigabytes per day of radar data. And from all of that data, we used statistical techniques, Bayesian networks in particular, to infer the structure of the models as well as the parameters inherent in the models. And those models themselves also went through several layers of verification and validation.
So lots of observation, lots of data. But all of us who have thought about autonomous vehicles are aware of what some people call the billion-mile problem, right? That accidents occur so infrequently. You simply can't collect enough data on accidents by driving a bunch of cars on the road. You simply can't assure that your autonomous vehicle software is reliable by collecting a lot of miles. So I think all of us as citizens and customers are going to demand that these AI systems are robust and reliable, not just against the situations we can test, but against the ones we can't or haven't tested. Do you want to talk a little bit about how we can create ways of assuring that these complex systems are even going to work in areas where we haven't yet tested them?
So can I start now? Yeah. Yeah, so automatic test case generation is actually an area that informal methods that people have looked at, and I think that could be applied for these autonomous systems. So it's not, for example, if I drive my car like a million miles on the same highway, right? If I drive that on Highway 101, that's not going to give me any information about driving in like downtown Palo Alto or downtown Berkeley, right? So it's important to automatically generate interesting scenarios and test in those interesting scenarios. So if you have good models, like it depends on having like again good models. If you have good models, we could actually like use these formal techniques to try to explore those models in all possible ways and come up with these like counterexamples, these difficult situations.
Yeah, very interesting. Mykel, in your talk, you talked about adaptive stress testing. And if I understood what you were saying, that's a way of synthetically identifying the space where code is not so robust or most likely to fail. Do you want to tell us a little more about how that works?
Yeah, so if you just do regular stress testing, you can, it's just an exhaustive variation of different scenarios. And you can absolutely find failure cases for TCAS and ACAS-X and so forth. But a lot of them aren't very interesting because they're super unlikely. So for an example, you can have two aircraft collide with each other if one suddenly goes at like Mach 3 at the other aircraft. There's no way to prevent that. And in the design of these safety critical systems, there's a very tricky trade-off between safety and operational performance. If we just wanted to be safe, then we just wouldn't take off. And that wouldn't be very satisfactory. And the FAA and other organizations understand that. The FAA has this safety management system, and they have identified threshold levels of safety that we're to achieve. So we don't want to just look at failure cases. It's important to characterize like under what scenarios will your system not prevent a collision or a safety critical event. But we want to find the most likely case that your system will fail in. And that's why I'm very interested in this area of adaptive stress testing. Turns out that you can also frame the problem of adaptive stress testing as a POMDP, which we do because that's what we do in my lab. And it can really effectively and efficiently find these likely failure scenarios without searching the entire space of scenarios.
I want to pick up on one of the things that Mykel was talking about, which is this idea of trade-offs. And I think All of you brought this up in one way or another in your presentation. Even if we can identify the desired outcome, even if we can go with this notion of a reward, it's often not a simple unitary thing, is it? Often we need to balance multiple things. We may need to balance efficiency and reliability and safety. In the insurance industry, I can imagine that you might want to optimize for a typical case or a worst case. So I'm wondering if we can delve a little more deeply into this question, that there may not be a single unitary good, but we may need to somehow balance a more complex, multidimensional space of desired outcomes and values.
I can take a crack at that. Yeah, I think within insurance, especially maybe let me take pricing, for example. So a lot of predictive modeling that goes into pricing, and you're constantly trying to balance, essentially this equity notion versus, privacy or social acceptance, cost. So we can price. Actually, we've experienced this before. We rolled out a new program several years back for pricing homeowners, and our group was so proud of this model. This was going to really just take property pricing to the next level. It took our agents over an hour to quote a single home because of all the data we asked for. So you can imagine how popular that made our group. This model is fantastic. It's just going to take you an hour to collect these 400 data points. And that was including a lot of public data that we were able to acquire. So that balance is definitely there within insurance. And then, of course, the regulatory agencies play a role in that as well. Variables that we would love to incorporate, but are just too darn sensitive or involve in sort of invasions of privacy that just can't be tolerated.
Anyone else?
Yeah, so similar problem. We have similar problem too. Like coming up with good reward functions for a robot or for autonomous system in general is really hard because there are all these different components and there are a bunch of weights. Like how much do you care about efficiency? How much do you care about safety? Or how much do you care about timing or expressiveness even? Like how much do you care about expressiveness? And they can affect each other because they're so dependent on each other. So coming up with these weights is difficult, and we have to and one way to address that is actually over time we can change the weight. So for example, if I'm not very confident in a specific situation, I think it's a risky situation, I should act more conservatively. So maybe I should care more about safety and less about efficiency. So we change these reward functions kind of online depending on what setting we are in. So that's one way to try to approach it. Another way that we also approach it is from this idea of learning from demonstration. For example, what we can do is we can look at how humans do it, like how humans drive. And from how humans drive, from that collected data, we can figure out what is a good reward function that at least the human follows and based it off that. So that's another way.
Did you want to comment?
Yeah, so we couldn't just go and ask a bunch of humans what their reward function is. Is it 2.3 or whatever? It just doesn't work. And the results of our simulations, we get a few dozen different kinds of metrics. And one of the interesting challenges with aircraft collision avoidance is that you pretty much just want one algorithm that works worldwide. And so you have a bunch of different stakeholders, and you want them all to arrive at consensus on the design of the system. And the different stakeholders, both in the United States and in Europe and so forth, they have different priorities on the different performance metrics. And arriving at consensus is super challenging, in part because of the burden on the humans. You can't just sit them down for hours and ask them, do you prefer this to that? And so you can actually frame the problem of what to present to stakeholders as a POMDP. There's a little theme going on here. And in the end, that's what we had to do in order to arrive at consensus on how to trade off these different performance metrics.
So if I ask you a question about MDP, will you buy me a beer later today?
Yes.
Why is MDP so critical for safe AI? What is it about that particular technique that resonates with the kinds of things we're talking about this afternoon?
So I think the critical thing that MDPs capture is the fact that the problems we face are sequential in nature, and that the outcomes are stochastic or random in response to our decisions. And in a lot of our problems, we also face partial observability. So the POMDP framework ends up being pretty important here in autonomous driving, in insurance, and so forth.
Excellent. I want to switch gears and probe another topic and then see if we have some questions from the audience. We've all heard a lot about the opaqueness of deep learning networks, that they're basically black boxes. And I think a lot of people are rejecting and rebelling against that. We don't want to turn critical functions over to black boxes. So there's been a lot of work on explainable and auditable AI systems. Talk a little bit about what that means, what explainable and auditable AI systems are, why it's important, why it's difficult, and what you're doing in your own research to accomplish this.
Okay, sir. Yeah. So when we say explainable AI, I feel like it's missing something. And that missing thing is, who is it explainable to? Like, is it explainable to the designer, or is it explainable to like some person who is using a robot in their home? And they're very different people, and explanations actually means very different things to them. Is it explanation, again, to the designer from a like debugging perspective, or is it like trying to tell like my mom like where the food is, like in the kitchen, or something like that? So I think both of them are very important. I think both of them are hard to get. And I think the first one is actually the one that a lot of like research like communities are thinking about, like explaining to the designer. And I've actually heard this from Mykel, so maybe the thing that maybe you should expand on that it's not just neural nets that are not explainable, right? And there is this thing in the community that neural nets are these black boxes, but there are other systems that are
lots of other systems
lots of other black boxes. So I think as long as we can diagnose where the failures are like in these systems, and we can somehow like verify them, like that would be a good way of thinking about debugging these systems and thinking about how to go about explaining them for the designer perspective.
However, you've commented that you'd like to create systems that can learn continuously based on their experience and the things going on in the real world. Mm-hmm. Does that mean we'll never be able to troubleshoot a system that fails? If my systems are constantly changing, then do I have the ability to go back and figure out how they managed to cause an accident a minute or an hour or a day ago?
So I think, so again, from the designer perspective, so we still have access. So as long as we have a full understanding of what is going on in the algorithm, we can go back and understand why it was doing what it was doing. From the user perspective, I think it's still like very interesting to kind of come up with explanations to the user of why did I choose to turn right here versus go straight. And even if we have adaptations, like we can explain adaptations to the users too, even in driving or in robotics. So I just wanted to make a differentiation between the two different explanations.
I would just say, I don't know that we've cracked that nut in terms of explainability of not just neural networks, but machine learning models in general. There's definitely things you can do in terms of feature importance and things like that. Sometimes we'll try and identify are there variables, like if it's still some sort of structured model as opposed to an unstructured model, or even unstructured model. Are there visualization techniques or other ways you can look at distributions of characteristics and features that can at least show you, okay, I can't tell you exactly how much this factor counts versus that factor, or why this one scored low, but I can tell you, let's look at distributions of what are your top 5, most important things. And it's, well, like in insurance, maybe it's credit score or the driving score or the age or the tenure of the business or whatever, and see how those perform.
So can you talk a little bit about how you do that? I can imagine that if I'm one of your salesmen, maybe you've created an AI system that tells me that when I'm on the phone with Dorsa, I should offer her an umbrella policy. She doesn't have one, but we know people like her tend to buy umbrella policies. So this is a great chance for me to earn some more commissions and sell some more insurance. Yep. Don't I need to know why to offer an umbrella policy to Dorsa? Isn't it insufficient to just know that I should offer it?
It's interesting because a lot of times they don't ask you why. until they don't like what it's giving, you know? So if they're happy with what's being recommended and if it agrees with them intuitively, a lot of times you don't get those whys.
It sounds like marriage counseling as well as
Yeah.
selling.
But one of the techniques we've used at different times is, you build these models, you use multiple techniques, and a lot of times we'll throw in like let's say we're doing random forests or neural nets or whatever, we'll throw in a logistic regression. If it's like a binary classification kind of thing, we'll throw in a logistic regression because that oftentimes will give you similar results, but yet it is very explainable. It's essentially a generalized linear model. And so at least it's not necessarily, you're not always going to get the exact same answer, of course, but if you can look at the performance of the models and correlations between the scores, you can get to a point where you can say, okay, here's the ultimate answer with this neural network, for example, but when I sort of retrofit this with a logistic regression or a GLM or something, I can see here's all these really important variables. And then you can kind of backtest that against the neural net and at least identify, do you see similar patterns? And it's not something hard and fast where if you're going to shoot some score to a claims adjuster and give that person the top 5 reasons, you wouldn't want to send those top 5 from your GLM because they could be totally wrong in any given case. But from more of a messaging and kind of informal perspective, it can go a long way toward, calming fears.
Rather than having my fears calmed, I'm now really worried because if the advice of what to do is coming from one model and the explanation is coming from a different model, what could possibly go wrong?
Remember, this is just insurance. No planes are going to crash.
Yeah, just insurance. Mykel.
So one thing that I've seen in my research is that when the computer goes to find a solution to a POMDP, what can emerge is superhuman decision-making performance. And I can think of several examples, actually, where the output of the optimization resulted in a system that I found very counterintuitive until I sat and thought about it for a very long time. And I think in the future of the AI, we will find that we need to, in some cases, make a trade-off between performance and explainability. And it's not clear how we should trade those things off. If it results in more lives saved, maybe we go with the superhuman intelligence. In other cases, maybe there are legal ramifications, like in insurance. Maybe we have to compromise on performance in order to get explainability.
Well, and this may take us back to the question of whether we want to be creating autonomous systems versus systems that augment and support human decision-making. But before we go there, let's see if we have some questions from the audience. Do we have any questions from the audience right now? Yes, we have a question right there.
I love asking questions. So it seems to me that to the point about cars and interfacing safety systems with cars, it seems like we're at a really dangerous junction right now where it seems like, at least in my own mind, I would trust a fully autonomous car in an autonomous world, but this interface between humans and machines seems particularly a dangerous point. In Japan, there's a concept, if I have it correct, Shisa Kanko, which is point and call, which is sort of a very rudimentary way of humans interfacing with complex systems to make sure they're paying attention to them. Some, for instance, trains and aircraft will set off alerts, not because something's wrong, but because they're trying to maintain the attention of the operator to make sure that they're paying attention to controls. And they have to respond or else the system will shut down or take other actions. And it doesn't seem like there's any of this in cars. And it seems like, and I'll also just note, I don't know whose research it was, but Shankar Vedantam, the social scientist in NPR, did this great story a month or two back, specifically about how humans were going to take advantage of autonomous cars by not letting them cut in, or a pedestrian would step into a roadway thinking the car would stop because that's how they're programmed, and forcing them to stop in ways that you wouldn't if you thought there was a driver behind the wheel. So I guess my question to all of you are your thoughts on, in this transitional time period from human drivers to autonomous driving, what's going to protect us? Because we're already starting to see obviously some failures, and I'm not sure whether those failures are any worse than normal humans crashing into people or not. But it seems like this is a particularly dangerous time period in the evolution of this technology.
So, okay, so a couple of things that we can do, right? One is better model humans, so we can actually, so our autonomous car in this case, like in the case that I was showing, does cut in front of people, like actually acts a little bit more aggressively. But actually that's more efficient because we're cutting in front of the person, you have this model and you're making progress and you're doing something that's more human-like. You're not doing this kind of like super conservative thing where people can actually take advantage of you. And that point that you were making, that's actually a great point, and that's really true like in robotics in general too. And we can think of that as an adaptation period, the fact that we adapt to these autonomous cars and we kind of build like human-driven cars are also going to build a model of these autonomous cars. So if they think the autonomous car is going to always slow down, maybe they actually like do act more adversarially and cut in front of them. Actually, I do that. Like whenever I see a Google car, I just like cut in front of it just to see what happens, just to give them some more data maybe. It'll be useful.
Probably expensive to fix. So
yeah. So another idea is also, so we want our cars to drive human-like. Also, maybe like using randomized algorithms could help there too. Maybe the car shouldn't always do the same thing. So make it a little bit more, still safe, but a little bit more unpredictable. So it doesn't, it's just an idea. It doesn't like always like drive the exact same thing. So you can actually take advantage, like you can't always take advantage of it. The other direction is this idea of having all fully autonomous cars like on roads where we are not actually in this period where we have shared roads, which is really hard to get, but that could be some future where we can imagine like a part of the city is all like fully autonomous, like have fully autonomous cars and there are no human-driven cars.
Mykel, tell us more about the need to understand the user and if there are different kinds of users, more disciplined users like commercial pilots versus perhaps unpredictable users like private pilots or vehicle drivers.
Yeah, good. Yeah, so my background has been in aerospace, but I joined Stanford about 5 years ago, and I wanted to see how much of this research translates to autonomous driving. And there are a lot of things we can carry over, a lot of things that are different. And one major thing that's different is that there's a wider variability in the training and expertise of human drivers. The human at the core is the primary source of uncertainty, and much of our effort is in modeling the humans and how to build a system that's robust to that.
So Mykel emphasizes that we need to understand the human. It seems like the human also needs to understand the AI system. And I would guess, Justin, that in your business, the people you're creating solutions for, you have to care about the mental model they have about your solution and how it works. Do you spend time coaching and teaching and training the users so they have the right model of your system?
It's a great question. And, we probably don't spend as much time as we should. I think, if I had a dime for every model that's rolled out to the business and maybe didn't have the impact that we had hoped or didn't have the acceptance we had hoped, I'd be a rich man. So you really can't undersell the value of that change management. Just the mere understanding, what is a false positive versus a false negative, and why. A really good example, actually, and I'll use it because one of the guys from AmFam is here who built this model, rolled out to our claims folks, and it was to predict claims that were headed like way south in satisfaction. So these were train wrecks. These were, we were likely could get sued, like going to be a consumer complaint, just very dissatisfied. And so these are really, really rare events. And we built what we thought was a great model, had great performance, but no matter what you do, this is only 3 or 4% of claims that are headed in this direction, and so you're going to have pretty high false positive rate. And fortunately, we didn't have a lot of the good sort of training and onboarding and change management up front. And lo and behold, a lot of these adjusters are getting this, thinking, not only well, this one looks fine to me, but also back to this sort of causal, kind of explainable perspective, it was very hard to produce that. And so the model has struggled, actually. If I could, actually, can I go back to the other question too? Because I really think, this AV thing and how do we go from where we are today to fully autonomous, I think we've got to do more and take more advantage of just virtualization and simulation. One of the things we're doing with another university,
It's okay, we know there are other
there
universities.
are other universities. We were looking to build a model to blur images from drones for safety, for privacy reasons. And so drones are at kind of an oblique angle. And of course, like Google Street View and a lot of the other solutions that are out there are Street View, are straight across. And so one of the techniques that this professor used was training from video game data. And if you think video games are a really, really, it's like simulation gone wild, right? And so when I think about autonomous vehicles, why couldn't we be doing more of this training of like construction zones and just crazy oddball situations that can be crowdsourced in so many ways. It can be crowdsourced into video games to create really, really rich training data sets without obviously putting any humans at risk. I think that's got to be, so we talked about it before, just the idea of crowdsourcing and simulation to create really, really broad, robust data sets has got to become a really big part of how we train and test.
Excellent. Thank you for that. We are unfortunately out of time. Please join me in thanking our panelists.